In this lecture, we will be talking about moments. I like this cartoon, it's funny. We have ways of making you torque. Ha ha ha, it's an engine, and torque is the same thing as a moment. So the two words can be interchangeable. By the end of this chapter, not necessarily this lecture, you'll be able to describe a moment, calculate a moment for a system of forces, express a moment using vector representation, describe couples, resolve a force into a force and couple, and simplify a force system. So we've already talked about equilibrium. In equilibrium, we've only really ever dealt with systems that are concurrent. In a concurrent force system, the sum of the forces is equal to 0, and that is sufficient to describe our system. So the resultant of two or more forces will produce the same effect on a body as the original system. This is maybe a new concept, but this is basically the same thing. We've been up to now calculating a resultant of this system of forces that we have. This is only, like I said, when it's concurrent. So when our resultant of our forces is equal to 0, we're in equilibrium, or we're in a balanced system. However, when we get into more complex systems, this is no longer sufficient. It's necessary, but not sufficient. So there will be additional pieces of information that we need to fulfill or describe our system. And that comes into play because of the point of application. In a concurrent force system, our point of application is the same for every single force that we have. So if we had a system of 3 forces like this, the point of application is all the same. Now, if we're working outside of a concurrent system, we can have a member that has forces being applied at all different locations. Now the difference here is that these points of application are important because when we apply this force, for example, it will tend to cause a rotation of this member like this. This is called a moment. So the tendency of a force to cause rotation is a moment. A moment is defined as a measure of the tendency of a force to rotate a body about a point or an axis. It is a vector quantity. What does that mean? That means it has magnitude and direction, not just magnitude. So when we talk about the magnitude of a force, the magnitude of our moment about some point 0 is equal to the magnitude of the force being applied times the moment arm. The moment arm our 0 is our point, which is our moment center. So if you see in this diagram here, if we have a point 0 and some force being applied to our system, the distance between those two, so we have a force, the distance between our point that we're taking the moments about, or 0, point of application, or whatever it is, the distance, the perpendicular distance, so you'll see these are perpendicular, the perpendicular distance between that point and where our force is being applied is what we multiply by to get our moment. Now what is the direction of that moment? The direction is described by using the right-hand rule. So if we take our right hand and we put our fingers in the direction of the force being applied, like in this picture here, the positive direction is where my thumb is. So positive is going to be a counterclockwise, and then our negative direction will be our clockwise direction. What are the units then for a moment? We are multiplying a force by a length. So in the English unit system, we would have a force times a length, or we could have force times inches, or in SI we would have Newton meters or kilonewton meters, for example. So the units for a moment would be foot pounds or pound inches or Newton meters or kilonewton meters. And yes, people will often call this a foot pound rather than a pound foot. So you'll hear those. So conceptually, let's think about things where a moment is applied. For example, when you're applying torque to a wrench, if you think about it, just conceptually, we all know from our intuition or our experiences that when you apply a force on a wrench, it's going to make it spin, right? So if I use my hand and apply a force to this wrench, it's going to make it spin in this direction. Now, which one of these is going to cause a greater torque? Just thinking about it, if you were loosening a lug nut on a tire, will applying a force directly against it at this distance away going to create a larger force? Or will this create a larger torque, or will this create a larger torque? The answer is this, and you can see this mathematically because, for example, if you are applying it at an angle, like is shown in this diagram, the only component that's actually perpendicular, which would be our force times distance for our moment calculation, we would only be applying the perpendicular distance of that force, which would be force times the sine of theta times d. The parallel force being applied is not going to create a moment, which you can see in this example. So if you are applying a force perpendicular to your d, think about pulling on a wrench that way. Are you going to create any rotation? No. So only the force that is created perpendicular to your member is going to create rotation.